So we've talked a little bit about the discriminant. Let's look at it in a bit more detail. So remember, it is, of course, that bit under the square root sign in the quadratic formula, so b squared minus 4ac. Now, it can tell us a lot about the quadratic without actually having to solve the quadratic. And I guess the first key thing we can look at, and we can work out, are the roots rational or irrational? If the discriminant is greater than 0, then we know that there's two different real roots. And if we're looking at the picture, that means it cuts the x-axis twice. Equals 0. Here's where people make the mistake. There are still two roots. It's just that they are the same. It's what's known as a double root. So there are actually two equal real roots. Yes, when you look at the picture, obviously it just touches the axis. So it has only one x. Well, do you still call it an intercept if it just touches? But anyway, I suppose you do. It intersects the x-axis. And when it's less than 0, there are still two roots. They're different, but they're not real. Now, as far as the extension course is concerned, we don't have to worry about imaginary roots. So we can just simply say, oh, well, there's no real ones. When we start looking at extension 2, then we worry about, okay, there are going to be two imaginary roots. As far as the graph's concerned, it just never touches the x-axis. If the discriminant is a perfect square, that's when the roots are rational. Because if it's a perfect square, we can find its square root. So we won't be left with plus or minus the square root or something. So they will be rational. Right, so we're going to describe the roots of 3x squared plus 5x plus 9 without actually solving it. So we'll find our discriminant. We notice it's negative. I suppose for the extension case, that's the boring case, because that just simply means, there's no real roots. So you can't really describe them if they're not there. So, no real roots. Boring. Let's move on to another one. Okay. 2x squared plus 6x minus 3. Find the discriminant. That is positive. So all the things we know about them. We know there's two, but there's always two. They're going to be different. They're going to be real. And they're going to be irrational, because we don't know what the square root of 60 is. So that's all the things we can tell about the roots of this particular equation. We've got x squared plus 6x plus k. We don't know what k is. But we want this equation to have equal roots. So what value of k? Two ways of approaching it. I can use this idea. Okay, so the equal roots, I know they're going to occur when the discriminant is equal to 0. So I'll just solve the discriminant equals 0. So 6 squared minus 4 times 1 times k is equal to 0. And we end up with k is 9. There actually is a quicker way of doing that. Right? Because if it has equal roots, then we know this must be a perfect square, because it only has one solution. And if it's a perfect square, I know it must be x plus half the coefficient of x all squared. So it would be x plus 3 all squared, and if I was to expand that out, 3 squared would be 9. That would be another way. That's probably the unusual way of doing it, but there's no reason why you couldn't do it that way. This would be the more popular way of actually using the definition of the discriminant. All right. What about if these roots are fantastic? So unreal. Another way of saying not real. All right, in that case, we want to find when is the discriminant less than 0. So we've got an inequality to solve. B squared minus 4ac, there we go, minus 4 squared minus 4 times 2k. And we end up with k is greater than 2. So as long as k is greater than 2, our roots will be imaginary or unreal or not real, or however we want to express it. This one has to have real roots. So what's the condition for real roots? That's where we've got to be careful, because we don't want to make the mistake of just saying greater than 0. It's actually greater than or equal to, because it might be that they're different roots, which is greater than, but it might be that they're equal roots. So that would be equal to 0. So greater than or equal to 0. B squared minus 4ac, play with that one. K squared less than or equal to a quarter. So k would be in between minus a half and a half. You You might think this is a rather odd question to place here, but actually it's not when you think about it. For what value of a, the line y equals ax going to be a tangent to this particular circle? All I really need to know when we solve them simultaneously, if it's a tangent, how many solutions should I have? I could just use the idea, hey, this equation, when I solve them simultaneously, so substitute in y equals ax for y, only has one solution. Well, if it only has one solution, discriminant must equal 0. So let's make it look like a quadratic. We've got something x squared, something x, and a constant. It will be a tangent, or have one solution, when the discriminant is equal to 0. So there's the equation we have to solve. Looks horrible, but hey, look, there's a common factor of 100 there, so we can divide by that. If we were smart, which I wasn't. Gosh, that would have been neater if I divided by 100 first of all, wouldn't it? Ah, good, there we go. Now I've divided by 100. We get 3a squared plus 4a is 0. We get two possibilities for a. A is either equal to 0 or a is equal to minus 4/3. What does that tell you about the circle? I'm more interested in the a equals 0. What must this circle do? Yeah, so y equals 0x. Oh yeah, y equals 0 is a tangent. Well, that's the x-axis, isn't it? Yeah, so it must be sitting on the x-axis. Ooh. Okay, time to play.